Goodness me, suddenly the quality looks really good and it sounds good too. Because it's... I lied. It's not a phone camera. What have I done? Chemistry. I've only done chemistry for like the past day, so... Everyone ditched me again. What do these people do on their holidays? Go outside? Please, they could be doing chemistry. For example, it's all organic chem, so it's stuff like... Are you ready for this? Like 3 carbons, actually 4 carbons, with like heaps of hydrogens. And if I've got 4 carbons like this, then it's obviously butane. It's fancy, but that takes ages to draw, obviously, so we tend to just go line, 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 like a squiggle, because each point is a carbon, and we just know that there's hydrogens there. But wait, there's also alkenes, so that's an alkane. It's known as saturated because there's as many hydrogens as you can have. But then, what about this? There's a double bond, so it's unsaturated, because the carbon will... Because carbons can only have 4 bonds. They only want 4 bonds. So instead of, these two will only have 1 hydrogen each, instead of 3 or 2. Then there's also the same thing, but with a triple bond. Bam! And that's an alkyne, spelled with a Y. So this is butane, this is butene, and this is butane. Then, there's other functional groups. For example, a hydroxy group, also known as alcohol. It's an alcohol group. So this is, how many carbons are there? 1, 2, 3, 4, 5, 6. So it's hexanol. Hexanol. Because it's got an alcohol group, so I gotta add ol to the end. Then you get on all these other groups. For example, there's a thiol group, which is sulfur and hydrogen, or an amine group with nitrogen. Then there's things where you can add a double bond to an oxygen. So this is an amide, as opposed to carboxylic acid. So this is, what, 1, 2, 3, 4. This is butanamide. This is going to be some terrible naming thing. This is butanoic acid. Then you get fun things like cyclic things such as benzene. Benzene. Look at all these double bonds. It's over here, and this is aromatic, so you can smell it. But wait, benzene's fancy, because this could be how the lines are, or it could be... I'm really bad at drawing hexagons. Could be like this. So these are known as resonance structures, because it could be either, and in actual fact it's more of an average, because that makes sense. So that's why we tend to just draw it like that. Kind of looks like a Lego piece. And then there's, I got so many sheets of paper here. What's another group? Esters. It's kind of like a carboxylic acid, but instead of having the OH, the H is just another thing. So there's this, which would be see, 1, 2, 3. So propyl, and then how many of these are there? 1, 2, 3, 4, 5, 6. Propyl hexanoate. Propyl hexanoate. Look at all these things. That's right, naming. There's naming conventions. So let's go back to this molecule. So, let's see, it's got 3 different functional groups. An alcohol group, an amine group, and a thiol group. So, I've got to say where they are, in alphabetical order, going for the most important one. So, from memory, the most important functional group out of these 3 is the alcohol group, then the thiol group, and then the amine. But we only care about the most important one, because we got to have numbers. So, because this is the most important group, we number from this side. So this is going to be carbon 1, and then carbon 2, 3, 4, 5, 6. So this is going to be thiol is a T, amine, we've got to name the amine first. The amine's on the 3rd, it's going to be 3 amino. Then with the thiol alcohol, oh my gosh, ALM. No, because it's hydroxy group, not just alcohol. So H versus T. So yeah, H come first. So 2 hydroxy. Where's this one? 1, 2, 3, 4, 5. 5 mercapto. Hexane? 1, 2, 3, 4, 5, 6. Hexane. Three amino 2 hydroxy 5 mercaptohexane. It's great. It's called IUPAC or IUPAC naming conventions or nomenclature. This is a lot of what I've been doing for 2 days, as in 1 day. And then there's all reactions and other weird things. Like, there's a thing I had to... Where's a good one? I've just got this book here that you can't see, full of all the chemistry. All the chemistry. Where's a good thing? I've got to draw out stuff too. Vesper theory and all sorts of stuff. Wow, it's weird. So, other things to do with chemistry. There's different ways of detecting stuff, like there's NMRR, and then there's other thing. Let's learn about shells. So, let's draw hydrogen like they draw for you in school. Hydrogen. It's got an electron, which is minus, and it's got one proton. Electron, proton. And its electron's kind of like a little particle, goes around in a circle. This is lies. In actual fact, it's more of a... It's supposedly in a shell, and it's like a probability is... The electron's here. It's like, as once heard it described as... So, you know in fairy floss, there's the stick, and there's all the fairy floss. And they're like, where's the sugar? Well, it's sort of there. It's everywhere. So there's these shells. The first shell is an S shell. It looks like a sphere. You can fit 2 electrons in it. One going up, or one spinning up, one spinning down. Because that's... You will not have 2 up or 2 down. Won't happen. It's not good for energy. So the electron configuration of hydrogen is known as 1s1, because it's the first subshell, and it's an S subshell, and it's 1 electron in it. So of course, as we go to, that's hydrogen, as we go to helium, it's known as 1s2, because helium has 2 electrons, it's still 1s. As we go further down, you get to stuff like hydrogen, helium, lithium. Lithium will have 1s2, but then still needs another 1. So the other electron will go in the second subshell, which is also an S subshell, 2s, and it's got 1. 1s2, 2s1. This is described by this, see, the boxes. These are S things. But if we wanted to go to oxygen, just so, oxygen has, what, 6 electrons? Plus, yeah, in its valence shell, its outermost shell. So, what, do we just have heaps of S things? No, we get 2 P subshells. Now, P subshells are shaped kind of like propellers. So these are actually 3. So you've got one going along one axis, like the x-axis, and the y-axis, and the z-axis, and that's not how the axes work. But yeah, and once again you can only fit 2 in each. Then the circle, the S's are in there. So, if we got the boxes, we've got, for lithium, sorry, oxygen. It's really hard to draw on the back of these. Then there's arrow. Then we need to get, so that's the first shell, that's full. That's sweet. So that's kind of like its own little helium. This is the valence shell. So we've got 1, 2, we need 3, 4, 5, 6. So fill, and by fill I of course mean half fill, because it's, but these will go 1 in each first, because electrons don't really like to be together. But they'll do it if they have to, such as in this case. We need to chuck in another one. Bam, and that's the electron shell configuration. Simplified for oxygen. And that'll be called 1s, 2, 2s, 2, 2p, these are p orbitals, 4. It's barely there. Then for something like the first gas, hydrogen, first, so of course noble gases, they have complete orbitals, shells. Orbital shells. So neon's the first one, so it's got to have all of these filled, giving a total of 10 electrons, and it's known as 1s2, 2s2, 2p, 6. I can hear Zach complaining about the chemistry. It's great. Eventually you get to things further down. As you get further down to stuff like where copper is, they've got to fill these d orbitals, which are really weird shapes, and they can hold 10. I think it's 10 electrons, 2 in each. Come on, I had to work it out for one of these. Wow, where did I work it out? Okay. So, yeah, and then as you get further down to where stuff like where lanthanum is, you gotta fill f orbitals as well. And they can hold like 12 or 16. 12. And it's fun. And because these are full, neon doesn't need any more electrons. It's got 8 in its outermost shell. It's like, I'm happy here. Don't need any, not gonna do any reaction, and it's almost impossible to get the electrons off neon. You can only do it further down at like xenon for the noble gases. It's cool, valence theory. So things like fluorine, all atoms want a complete shell. Fluorine has, let's go back to terrible, not true way of doing stuff. So 1, 2, 3, 4, 1, 2, 3. Fluorine has got like 7 in its outer ring, so it just needs 1 more, so it super wants it. So that's why it's super electronegative, which is its strength of pulling stuff. It's like almost 4 It's 4. There's no unit. I tried googling it. It's sad. Now francium, on the other hand, it is an alkali metal. Wow. The things on the far left, they're the ones that when you chuck them in water, don't chuck them in water. When you chuck them in water, something, particularly things like cesium or francium, which are pretty far down, you get something kind of like this. A chef's hat. So francium actually is super far down. It's got like an absurd amount of shells that are full, so it's huge and really unstable because that happens. But the point is, in its outermost valence shell, it's got 1. So it's essentially like when francium sees something, it's just like, take the electron, take it, take it. That's why it's super reactive, and why if you chuck it in water, it's the end of the world. But there's only like a few grams of it, a few hundred grams of it existing on the Earth at any one point, because it has a half-life of like 22 minutes. So after 22 minutes, half of it's gone. Not as bad, though, as the alpha daughter of it. So what it decays into during alpha decay is astatine. Whatever it is. Astatine. Which has a half-life, one of the types of it, of 56 seconds. So it's like, hey, check out this cool thing, and you start up your laptop and it's gone. And that is enough chemistry for today. I'm sorry that this wasn't in 16.9 because I can't do it. This actually looks like it almost is in 16. Oh well. Sure, maybe next week, when there's no longer uni holidays. Then, maybe people will be back. We'll see. Till then... yes. I like how I just hit the stop button and nothing happened.